We're going to be talking right now, the first thing we're going to be talking about is three gates: AND gates, OR gates, and NOT gates. AND, OR, and NOT. Now in AND gates, we always refer to that A and B, A and B. But instead of writing the word AND, we use multiplication to write that. You go A and B. So when you see that, that's an AND gate.
That's not a multiplication. That means and.
Which one? That, yeah, the dot?
I'm just trying to.
Yeah, that means AND. So instead of the word AND, we use the dot like a multiplication symbol.
But it's not multiplication.
Well, if you look at the truth table, it looks like a multiplication because the truth table for that, if you have A, and if you treat it as multiplications, A and B, that's called the truth table. When both zeros, 0, 1, 1, 0, and these are all four options, and 1, 1. What is 0 times 0?
0.
What's 0 times 1?
0.
What's 1 times 0?
0.
What's 1 times 1? That is actually the truth table for the AND gate. That's why they use the multiplication to indicate. But it's not really multiplication. It's a symbol for multiplication, but you're not multiplying like real multiplications. It's not 1 times 1. But the truth table works in that sense. It looks like you're multiplying the numbers. But that's the truth table for the AND gate. The OR gate, when you write A, go A or B. Again, we don't want to write the word OR. We use addition. And if you look at the math, it looks similar. I didn't say exactly, it looks similar to that. Why? What's 0 or 0? What's 0 plus 0? 0. What's 0 plus 1? 1. What's 1 plus 0? 1. What's 1 plus 1? Now 1 plus 1 is normally 2, but here is actually 1. So an OR gate, it's not a straight addition. But we use the symbol addition to indicate that's an OR gate. So for an AND gate to be 1, that means both of them have to be 1. For an OR gate to be 1, at least one of them has to be 1. Now the NOT gate is the complement. We use this one. You either write not A or A with this, and that's more common than this one. The reason that's easier to write in a textbook, because on the keyboard you look for what? Single quotation. So to write that, that's easier, but to write this, that's more challenging. So a lot of people use this instead of that, but that's really the common one, but because it's difficult to write, everyone goes with that notation.
That means complement, right?
Complement, yeah, it means complement. Complement. So when you have the truth table for that, if this is A, this is the complement of A. When A is 0, what's the complement of 0? What's the opposite to 0? 1. When A is 1, what's the complement of that? 0. So these are the truth tables for AND, OR, and NOT gate. I'll give you a chance to write them down. Now, how do we draw them in our circuit? That's not what the inside of them looks like, but the way we draw the AND gate, we go A, B, straight line, not curve, straight line. That's an AND gate. Some people put a dot to say that's an AND, because sometimes people, when they draw them, that line might look like crooked, and people are not sure if that's AND or OR. So that's A and B. So when you draw an AND gate, this is what we use for a picture for an AND gate. I usually don't put the dot in them. You know, I try to make my line straight, so you'll never see me put a dot in them there. I'll go like that. An OR gate, when you draw an OR gate, the difference, this is bent, like this. See the difference? This is straight, that's bent. When you bend this edge, that's an OR gate. That means A or B. And the NOT gate, this is A, and this is the complement of that. That's what the NOT gate is. You'll see, we'll probably go to the lab next Thursday. When we go to the lab, you will see they don't come single gates. They come on a chip. And we'll have either 4 of them, or we'll have 3 of them, or we'll have 2 of them. Why? It depends on how many inputs. Now, again, let me show you the difference between the AND versus the OR in just English. If I said to you to get A in this class, maybe I shouldn't say this on video. Let me change what I was about to say. You have to have an average to get A in this class. You need to have an average greater than 93 or a score of at least 95 on the final exam. That's not true here, by the way, in this class, but just for the example. Now, if your average at the end of the semester is 94, let's say you got 100, 100, 100, 100, and on the final exam you got an 80. Your average now is 94. Do you get A in the course?
Yeah.
Yes, because your average is bigger than 93. Or you failed every test along the way. You got a 0 on every one of them, or you didn't even show up for them. But you took the final exam and you got a 97. Do you get A in the course?
Yeah.
Yes, because this one says you don't have to do both. You only have to do this one or do that one. If you want to do both, that's even better. But you only have to satisfy one of the conditions. That's why 0 or 1 is actually a 1. As long 1 means yes or true and 0 means false. True or false. So when you look at it, basically the conditions A and B so if you have false and false, it gives you false. Once one of them is true, false here and true, looks like a true here. True and false is true. And if they're both true, you met both conditions, that's still true. So if this condition was false and this was false, your final answer is false. That means you're not getting an A in the course. But if one of these conditions is true, I have to give you the A. If they're both true, I have to give you the A. Now the AND, so we're talking about here, OR here. To get A in the course, that's an OR here. An AND, if I change that to get A in this class, you need an average of greater than 93 and, let's say I said and instead of or here, final exam score is bigger than 95. What happens? Let's say you got a 97 average, 100 average. You got 100 every single test. You take the final exam and you get a 94. What happens? You're not getting an A. Maybe A minus, but you're not getting an A. Both of these have to be true. Both of them. So with the AND, if you have false and false, the result is what? False. false and true, the result is false. True and false, the result is false. The only way to get a true result is what? Both conditions have to be met. Both have to be true. So that's the difference between and versus or. Now, when you're adding numbers, let's think about just pure math here. I said to you, when we get these chips, sometimes there are or maybe 3 of them on one chip. It has 3 OR gates. It says dual. It has quad. So a chip here, a computer chip, we'll see them in the lab. It looks like this, has a dot on it, has legs on it. Something like this, and you connect it. And that chip inside, it might have 4 gates, 4 OR gates, or 4 AND gates. We call it quad 2 input OR gates, quad 2 input AND gates. They put 4 of them. First, to power that chip, they're going to make you, one of the input has to be VCC, which is like 5 volts. The other one has to be 0. And now what they do, they take this, let's say an AND gate, and that becomes the output. Then they take this, and that's this one. Might be another one, probably like 16 pins on it. They take 2 of these here. And they'll take 2 of these. And one has to be attached to VCC, one has to be attached to ground. I got 1 extra connection here. So one of these pins will be attached to the voltage, like 5 volts, and one will be ground to power that chip. And once you have that, you have 4 of them on that chip. If they're using a 3 input gate, then we have a problem. A 3 input, you can't fit 4 of them. So what they do, they need 3 inputs to make 1 gate. There goes 4 pins right there. So they might go like this and take one from this end to make another one, and they take another one here, and you have to power it again. So you'll have 3 of them. And the ones with 4 input OR gates, you're going to need 1, 2, 3, 4 just to make one of them.
What's the SV? 5 volts.
5 volts.
And that 0 is ground.
Yep. So it will look like this. So our chips in the lab, these are going to be a quad, that means 4 of them. If there are 2 inputs. If there are 3 inputs, going to be 3 of them. If there are 4 inputs, going to be 2 on each chip when we're in the lab. So we have to be careful. So what will happen, sometimes I don't have enough chips for everyone. So what happens? Let's say I want a 4 input OR gates. So this is what the chips will look like. And again, it has all these legs on them. So mathematically, I want to create now a 4 input OR gate. Or I have this expression. And I go, I don't have any 3 input OR gates. We know that's 3 input OR gate. But I don't have a 3 input OR gate. How can I add them? Think of math. If you were to add 2 numbers, how can you add them?
Add A and B and then AB plus C.
Sure. You can write that A plus B, get your answer and add to it C. Or you can go A plus, add B and C, and add the result to A, right? So if you need a 3 input OR gate, but you don't have one, you only have 2 input, you can take one with 2 inputs. There's A and B. When you get the result, what do you want to do with it? Add it to C, and now that's a 3 input OR gate.
That's cool.
Yep. The reason you want to do that, because sometimes on that board, you have a chip that's a 2 input. Maybe you use 2 of the gates, and you still have 2 more gates freebie, and you need a 3 input. Why should I add another chip to that board? It's going to cost me another $1.50 when I can grab it and use that one I have right there. Or sometimes you want to have 4 input OR gates. Could be AND. I use OR, but it could be AND. And I don't have these. What is A plus B plus C plus D? That's what we're looking for. Well, we know you can write that A plus B plus C plus D. So you can take 2 inputs, OR them together. You can take another 2, OR them together. Take the result and OR it back together. What's the advantage of this over this? Or what's the advantage of this over that?
First one's faster.
First one is faster. Gates have delays. It might be 2 microsecond. There's a 2 microsecond delay. This one's going to be 2 microsecond. Well, these guys are the same time, so there's 2 microsecond for them. But now this also is going to have what? Another 2 microseconds, so you have 4 microsecond delay. So by the time the result comes out of this, you delayed it twice as long as that one. But if that saves me in time, if I'm looking for speed, I'll go with that one. If I'm looking maybe for cheap design, I might have these on the board and I can steal them without having to put another chip, and then my design will be cheaper. So it depends what we're looking for. If I have some with 4 inputs, some with 3 inputs, and I go, I'll use OR and AND, I'll mix and match. I have a 4 input OR gate. That's 4 of them. But I want to use this for this one. That's a 3 input. The gate I have one on the board, an extra one sitting that has 4 input. What am I going to do?
Well, it's an OR gate. You can just not hook one of the inputs up to anything.
Not hooking is not a good idea. I mean, it will work mathematically, but there's a safer way because you don't want to leave anything floating there.
Just use one of them twice.
I can use one of them twice, sure. I can take this. Okay, you know what? That A, connect it to both of these. You don't want to leave it blank there. It looks like an antenna. It picks up some noise. So you're trying to eliminate all the noise. So by taking, it doesn't matter which one, you take one of them, hook it twice. If you don't want to hook one of them twice, another option, or what do we do with this? Ground it. Don't make it a 1, because if you make it a 1, guess what happens? With an OR gate, the result becomes what? Always a 1. Once one of them is true, everything's true. Regardless what these are, if you make it a 1, this is always 1. So this will not work if you make it a 1. If you make it a 0, that'll work fine. So whatever A, B, and C. If it was an AND gate, again, and you have 4 input AND gate, yes, you can do hook one of them to both of these. I'll make it C this time. I don't want it to be always the same one. So I can do that. Attach one of them to both pins so it's not floating there. Or if I don't want to attach it to both of them, what can I do?
Ground it.
You got a trouble. If you're grounded, you're in trouble. An AND gate, once you have a ground, guess what your output is? Where's an AND gate? It's always a 0. You just killed it. So what do you want to do then? Make it a 1? Sure. Make it a 1. So you take this one, make it a 1. VCC, which means 1 here is high voltage really in the lab. When we're in the lab, whatever the high voltage. For our equipment, the one we use, that's a 5 volts. 5 volts means 1 high voltage, 0 volts means 0. So 5 means 1, 0 means 0. High and low. Some of the gates, by the way, they work backward. You'll see like reverse. Like 0 is high and 1 and 5 is low. We'll talk about those too. Let's look at some. Sometimes you have an expression that's like this where I can shrink it. Let me look at that. Let me just write one expression here. And I said, I want to build this one in the lab. W bar, because I find it easier if I write them on the top. X, Y, Z bar plus W, X bar, Y bar, Z bar plus W, X bar, Y, Z plus W, X, Y, and Z. You want to build this one in the lab. If you were to build this without simplifying that, that's an AND gate, AND gate, AND gate, AND gate. So you have 4 AND gates. I'm assuming even the NOT is available for you. Usually the NOT is not available for you. So if you were to build this in the lab, this is what you have to do. Let me make it nicer, actually. Let me make it look nicer. And maybe have some graph paper here. This is where the time consuming becomes. When we build these, actually, to give it to the technician, it better be straight, better be almost perfect, otherwise you get it back. The guy can't read it, redo. And that's why you see us sometimes stress out, like make sure you do the problem correctly. Make sure you do it nice and neat. When we assign homework, sometimes we give it back to you, it says like, it's not neat, because they want you to have the problem neat. So if I want to graph this, I want to design this for somebody, I'll go, well, I got 3 inputs, W, X, Y, and Z. I notice there's W bar, right? This has W, X, and there's X bar, so it's both of them. There's Y and Y bar, there's Z bar. So to design this, here we go. There's my W. Let me know if you can see that. And I'll run a line like this. Can you see it? Yep. I can actually use just a pen instead of a pencil. Normal pen, standard pen. Here we go. So this is the W. Is that better? Yep. And what I will do here, right next to it, I'll get a NOT gate. And that becomes what? This piece is W bar now, because I'm going to need it. That's W and W bar. Then I need another one here. W, X, Y, and Z. Let's do X here. This is X.
X has 2 NOT bars.
Huh?
Does it matter if it has
Nope.
2 NOT bars?
Nope. You'll see how we're going to do that. This is X bar. That means anytime I want X bar, I can grab it from this wire. In the lab, when we go to the lab next week, you'll see we have these called breadboard, where we can attach X and X bar to them. And I have Y, third one. That's Y. And let's do Y bar. And one more. And Z bar. So now I got all my inputs ready. How many AND gates do we have? 4? I have four terms, 4 AND gates. So let me draw an AND gate. I don't like this one. Let's do a black one here now. Here's my first AND gate. There's the second one. There's the third one. And there's the fourth one. I got 4 of them. What's attached to the first one? Where's my expression? Here we go. W bar. So here's W bar. And you put a dot here. That means it's attached. That's W bar. X. Oh, I went too far with it. X is attached right here. What else attached to it, the first gate? Y. And the last one is what? Z bar. Z bar is right here. That's the first gate. So if I make this my output right here, this is W bar, X, Y, Z bar. The next gate, W, not W bar, W. So you go all the way to W. Remember we said the stuff takes a long time? Just connecting these. X bar. Y bar. And Z bar. That's the next one. So now this one here, it's W, X bar, Y bar, Z bar. Next one, W. X bar. Y and Z. And Z. That's the next gate. One more. W, X bar, Y, and Z. And the last one, W, X, Y, and Z. There are no bars on it. So everything is straight. W, X, Y, and Z. And we got the other gate.
What is this called?
What do you mean?
The diagram itself.
Nothing. When I said design it, implement or design, that's what you have to give to the technician. This is how I make my lab. Now, I'm not done with this because this is what? What happens, the plus sign between them, what does that mean? Take all four of them, OR them together. So I need an OR gate here. So I got to make sure these now come down here. This is what computers engineers do actually when you design something. 9 out of 10 times, you're not the one putting it together to ship out. You put it like this. Actually, you go on a computer, and the computer will tell us what the best, there's a program that will tell us what the cheapest way, which way to put them on the board. Should I put them sideways, up and down, what kind of board to use? That will save us some money. But this is what we have to design to give to them so they can figure it out. Just like a blueprint. If you're into construction, you want to build a house, the engineer comes in and does the blueprint for them. Then the builders will take the blueprint and read that and implement that. And that's what we're doing. We give them the blueprint for our design, and that's what our function is going to look like. Well, I need 4 NOT gates. See them? Can you see them? That means 1 chip on the board. I need what? This is 4 input. That means 2 chips on the board. They come 2. So there's 1 chip. This has 8 of them actually, the NOT gate. This 1, 2 chips, and there's 1 more.
3.
So I have 4, because this is 1 chip and that's another chip. There are no 4 input OR gates. So you have 2 here, that's 1 chip. There's 2, that's another chip. There's 1 chip here and there's 1 chip. There's 4 already on the board. That board already costs you about $6-7 right there with no labor. Just the gates. Then you get the plastic under it, then the labor and connect them. Sometimes you can actually take that expression, simplify it, if you know how. If we know how to simplify this one, I can eliminate probably 3-4 of these things. It might even be straightforward with something else. And that's where we're going with this. It's called Boolean algebra. How do we simplify? How do we take an expression like this, simplify it, and see what will happen with it? Yep. So let me stop the video here.